Hi everyone, it is still your one and only Gmaets 41. You are welcome to my channel. So in this video, I'll be teaching you one interesting phenomenon that takes place when light refracts. We're looking at the concept of critical angle and total internal reflection of light. You see, this phenomenon is observed when light travels from an optically denser medium to an optically less dense medium. Simply put, when light is moving from a denser medium to another medium that is less dense. And just for purpose of clarity, when you hear the concept of denser, that goes with thickness. Almost so, we can think about the concept of, what is called refractive index, the quantity known as refractive index in the study of refraction of light. So when light moves from a medium that has higher refractive index to a medium that has a lesser refractive index, there is this certain angle which, if you cross, this phenomenon known as total internal reflection will take place. But before we study this concept of total internal reflection, we should know the meaning, the concept of critical angle. Yes, it's important for a scholar to understand what critical angle is, because that critical angle, if you cross it, that is what leads to total internal reflection of light. So once again, I welcome you to this wonderful channel. And if you are yet to subscribe to this channel, please click on the subscription icon. Then go further to turn on the notification bell. Personalize your subscription so that once I upload any content, right, or I go live anytime, of course, Gmaets 41 always have live classes. So whenever I go live or I upload any content, you will be notified right away by YouTube. Don't forget, you can also become a channel member so as to support Gmaets 41 on monthly packages, platinum level or diamond level. And this gives you further benefit from this channel, especially video lessons, classes that are meant specially for channel members. You have the join tab below this video. You can click on that join tab and then the packages appear. Select either the platinum or the diamond package so as to benefit more from this channel. So let's get into business, okay? In the study of this critical angle and total internal reflection of light, we consider semicircular prism. Semicircular prism. So the prism is not rectangular, it's not triangular, rather it is semicircular. Let us take a look at this semicircular prism here as we have it here. Can I see? Good. So this is a semicircular prism. You can see half a circle. Now this semicircular prism compared to the surrounding air, we say that this prism is thicker. This prism is thicker. If this prism is thicker, it means it is denser. It is denser. It has, a higher refractive index compared to the surrounding air. So we want to look at a situation where light travels from this semicircular glass. So light is coming from it to the surrounding air. Now we know that when light crosses a boundary between two media of different density, that light will bend. That is what we call refraction of light. So in the same way, if light is coming out from this semicircular prism to the surrounding air, right, it's going to bend because the surrounding air is less dense than this semicircular glass, right, semicircular prism where the ray of light is coming from. The light ray, once it enters the surrounding air, will bend away from the normal. Take note, we bend away from what I said, the normal. I've got a video lesson that explains the principle of Snell's law, that talks about the angle of incidence, the angle of refraction, and the normal. at the point of incidence, they lie on the same plane. Okay, that is first law of refraction. Then second law of refraction, that is called Snell's law, particularly talks about the sine of angle of incidence. Its ratio of sine of angle of incidence to the sine of angle of refraction is constant for a given pair of medium, and that constant is called the refractive index. This info link will direct you to that video lesson I just made reference to, so that you can learn more about the concept of all these rays. Although you still see some of them as I show them on the board. So let us get to business. This is a semicircular glass. Now look at the normal. The normal is simply a line drawn at 90 degrees to meet that prism. Now let us have a ray of light coming from this direction, okay? So it is in the glass, so the ray of light moves at the point of incidence. That is where it strikes the boundary between the prism and the surrounding air. You know, you have the edge of the prism here. Coming out is the surrounding air. So as the ray of light comes this way, hits that interface before getting to the surrounding air. You now notice that on getting to the surrounding air, it bent. So watch, the ray of light bent away. It bent away from the normal. It bent away from the normal, as if it's going towards the prism. Okay, this refracted ray is a strong refracted ray. There is something that happens here. There is a corresponding reflected ray. And look at it. That reflected ray goes back into the prism, because of course that's what reflection does. Take note, reflection is also a property of light or wave. Refraction is also a property of light and or wave. Okay, so if you hear refraction, reflection, don't get confused. These are two different properties of behavior of light wave, right? So as this ray of light comes out, okay, into the surrounding air, it refracts, bends away from the normal. And this is because the light is coming from a denser medium, which is this semicircular glass, moving into a less dense medium. If light travels from denser to less dense medium, the refracted ray will bend away from the normal. But if it is moving the other way around, that is from less dense medium to a denser medium, it will bend towards the normal. We label that incidence ray inside this prism as I1. Let this refracted ray be R1. Let this reflected ray, I'll be using L for reflected ray, let it be L1. Now, we progress again. I am going to shift the incidence ray. You know, let's increase it. So watch another ray of light. You know, this way. And then it falls on that interface between the denser medium and the surrounding air, the point of incidence. Again, you notice that the ray of light bent away more than the first one. It bent away from the normal. A strong refracted ray. But you now observe that this refracted ray, which I am going to label as R2, is much more closer to the interface. That is the boundary between the semicircular prism and the surrounding air. There is a corresponding reflected ray, and the reflected ray is weak in this case because the refracted ray is strong, because there is a clear refraction here. Interesting. Let us go further now and see what happens. We are still going to increase the incidence angle. The incidence angle in the denser medium, in the semicircular prism. We're going to increase that angle now and see what the refracted ray is going to do. We're going to see the positioning of the refracted ray. So now and again, we have this incidence ray coming from the denser medium. So at the point of incidence, you now see the refracted ray. The refracted ray now is purely parallel to the interface, the boundary between the denser medium, which is a semicircular prism here, and the surrounding air. As a matter of fact, if you watch this refracted ray, you notice that the refracted ray meets the normal at 90 degrees. You can see that. It's something like this. This is the normal, and then the refracted ray goes this way. So the angle here is 90 degrees. The angle here is 90 degrees. So this refracted ray that is at 90 degrees to the normal at this point in time is significant. Is significant. The angle of incidence in the denser medium, in the semicircular glass, that produced a refracted ray which is perpendicular, which is at 90 degrees to the normal, is the angle we call the critical angle, which in this case is I3. I3 is the incidence ray. The angle of I3, as you can see inside that semicircular glass, that angle that the incidence ray made with the normal in the denser medium, which produce a refracted ray that is 90 degrees to the normal, that incidence angle is what we call the critical angle. So guys, I hope you capture this idea of critical angle. The critical angle, based on what I just explained here, is simply defined as the incident angle in the denser medium when the refracted angle in the less dense medium is 90 degrees. So anytime you incident light from a denser medium and then the refracted ray produce an angle of 90 degrees, that angle of incidence that produced that refracted ray of 90 degrees, that angle of incidence is called the critical angle. And I hope I've been able to make this idea of critical angle very clear to you. That's good. Having explained this concept of critical angle, it will now take us to the phenomenon known as total internal reflection of light. Remember, at all cases, R1, R2, R3, R3 is the refracted ray, which is 90 degrees to the normal. For all of these cases, we had a weak reflected ray. That is saying the light bouncing back into the denser medium. Light came from the denser medium. At the point of incidence, we had a weak reflected ray, a ray that went back into the semicircular prism. We said that one is a weak reflected ray. What will happen if I increase the angle of incidence further? What if, like I said, I incident another ray from the denser medium? This time I4, incidence ray 4. But this incidence ray, the angle of incidence is now greater than the critical angle. That is to say, the incidence angle in this case is more than, exceeds the critical angle. So watch, these are I4. So you can see the angle at the point of incidence in the denser medium. Let us see what the refracted ray is going to be. You can watch. In this case, we no longer have any refracted ray anymore. All the light ray will now be reflected into the semicircular prism, because in this case, the reflected ray, as you can see, L4, is now a strong one. So we have a strong reflected ray. We have a strong reflected ray. Observe that I4, the angle I4, that is the angle that incidence ray 4 made in the denser medium, is now greater than the critical angle. You notice that all the light rays were totally reflected back into the prism. This is what we call total internal reflection of light. So if you're asked to define that phenomenon, what is it? So we define total internal reflection of light as the reflection of light ray at the interface between a denser medium and a less dense medium, when the angle of incidence in the denser medium exceeds, is greater than the critical angle. Once again, total internal reflection of light is defined as the reflection of light at the interface between a denser medium and a less dense medium, when the angle of incidence in the denser medium exceeds or is greater than the critical angle. So these two key concepts in the study of refraction of light is important that a student take note of. The concept of critical angle and total internal reflection. And I hope I've been able to really make these concept very, very clear for you. Please take note. That is referred to as total internal reflection, not refraction. Even though this phenomenon, this occurrence, takes place under refraction of light. But what really happens whenever the angle of incidence in the denser medium is greater than the critical angle, the bending of light in that case is no longer refraction, but it is called reflection. And in that case, the light is totally internally reflected because the light went back into the denser medium where we had the incidence. The light still went back into it. So it is said to be totally internally reflected. This is interesting, guys. I hope you've learned something cool. Now, what is the formula for the critical angle? What is the formula for the critical angle? We're going to apply Snell's law, which is the second law of refraction. Okay? And you watch as I do the analysis on the board. Now, from what we've just explained, apply Snell's law, which states that the ratio of sine of angle of incidence to the sine of angle of refraction is constant for a given pair of medium. The medium we have here is, the semicircular prism and, of course, the surrounding Earth. So we are going to have that sine I over sine R is equal to the refractive index. Is equal to what? The refractive index. But remember that the light traveled from a denser medium, which is the semicircular prism, to a less dense medium, which means that the refraction took place in the less dense medium, the surrounding Earth in this case. Therefore, if I write sine I all over sine R equal to the refractive index there is going to be the refractive index of air. And so I'm writing sine I all over sine R equal to N. And then this N, you have GA. This GA means light is traveling from glass to air. Where light is going to, where light is traveling to, that is where refraction takes place. And where the medium where refraction is taking place, that is the medium whose refractive index we quote. So since light is traveling from a denser medium, the semicircular glass, to a less dense medium, air, refraction takes place in the air. Therefore, sine I all over sine R will be equal to the refractive index of air because the refraction took place in air. Now, at critical angle, remember, we learned from the explanation that the angle of refraction will be 90 degrees at critical angle. The angle of refraction will be what? 90 degrees. And you know the critical angle is angle of incidence in the denser medium. You saw all of those as I explained that. Of course, you can still see the diagram here. Therefore, the sine I, that I, we're going to change it to C, which is the critical angle. So I have sine C all over. The refracted angle is 90 degrees at critical angle. So in place of that sine R, I'm going to fix sine 90. So we have sine C over sine 90 equal to the refractive index of the air. Sine 90 is 1. So this is simply sine C equal to refractive index of air, of the medium that the light traveled into and refracted. Remember, the light ray came from the glass, of course, the denser medium, which is the semicircular prism, and then moved into air. And that is where refraction took place in air. So we simply have sine C equal to the refractive index of air. Now, in most cases, generally, refractive index of air is not usually quoted. We have refractive index of other medium. Okay, so this is what I want us to do, which is what you are meant to know. You have to convert the refractive index of this air to that of the prism. And how do we achieve that? Using the principle of reversibility of light. If I pass light straight this way, and then someone now focuses that same light from that direction, in that way, it will follow that same. Watch, I send in light like this, maybe it met a refracting surface and then it bent this way. If you focus light from that direction, this direction, now this way, and it meets a refracting surface in that same direction that it refracted, that light will come back this way exactly, which means forward direction, the same backward direction, they are the same. We refer to that as the principle of reversibility of light. For that purpose or for that reason, if I tell you that light is moving from this material into this material, and the refractive index of this material is A, the refractive index of this material it is entering will be 1 over A. What does that mean? Light is moving from one medium to another medium. The refractive index of one of them is simply inverse, reciprocal of the other one. Coming back to this analysis, since sin C is equal to the refractive index of air, light is traveling from glass to air. So if I know the refractive index of air, the refractive index of glass will simply be 1 over that of air. Which means that the refractive index of the air will be equal to 1 over that of the glass, that of the semicircular prism. Therefore, I am going to remove the refractive index of that air and fix 1 over refractive index of the prism. So the formula becomes sin C, that is sine of the critical angle, equal to 1 all over refractive index of that prism. Because when questions are given to you, the refractive index of the glass, of the denser medium, is usually being quoted. Yeah, it's usually being quoted. And of course, this is a wonderful formula. You have to memorize it. Sin C equal to 1 over n. We are just simply using that n. That n is actually n AG. That AG means light traveling from air now to glass, reversing the process. Okay, but without wasting our time, let that refractive index of AG, light moving from air to glass, let's just call it N, because that's how you see it in different sources. If you study, your books, you browse, and other things. So we have sin C simply equal to 1 over N. Where you want to take note, that N is the refractive index of the denser medium, where the light is coming from. Good. What are the conditions for total internal reflection of light? For that to happen, what are the conditions that must be met? There are 2 conditions and you need to know them. Condition number 1, for total internal reflection of light, light must travel from an optically denser medium to an optically less dense medium. Simply put, light must travel from a denser medium to a less dense medium. That's condition number 1. Then condition number 2, for total internal reflection to occur, the incidence angle in the denser medium must be greater than the critical angle. These are the 2 conditions for total internal reflection of light to take place. In conclusion, what are the applications of total internal reflection of light? One is our mirage. Have you heard of mirage before? Mirage. You are driving on a smooth road on a sunny day, a clean express. On that sunny day, you view ahead of you on the road as if there is a pool of water. But as you drive close, the pool of water continues to disappear and disappear. You just can never get to that pool of water. That is mirage, something that is faked. So that stuff is an application of total internal reflection of light. Another application of total internal reflection of light is the field of view of fish. Fish have eyes by the side, and the eyes is a bit curved-like because it's a convex lens in nature. So the part we are seeing is curved, just like this semicircular prism. Somewhere here. Why is it that if someone wants to attack fish from the top, like from the head directly, the fish will actually get to see that something is coming and take off? If fish is moving inside water, like, you can hardly pin it down like this. If you try to do that, the fish will take off. How come? How did it get to see you? Due to total internal reflection of light. Once you come in that way, as you enter into water, water is a refracting medium. So it's going to bend, right? The ray coming from whatever you are using to want to pin the fish, it's going to bend it towards that direction. Total internal reflection will take place. So as that is totally internally reflecting this way, from this edge, the fish picks that there is danger, something coming. God has so designed them wonderfully. Seeing that he knows someone wants to attack, and immediately it takes off. So that is another application of total internal reflection. And guys, this is the much I just want to explain to you and teach you from the Gmaets 41's platform. And I hope you learned something wonderful. Share these videos to your friends, okay, to your classmates. You can share to your WhatsApp groups, and then encourage them to subscribe to Gmaets 41's channel. Like I've always said, this is a wonderful channel that is dedicated to giving students the best at all times in your STEM subjects. All right, physics, chemistry, mathematics, you can always count on this channel. And don't forget, if you have challenges with your basic level of learning, is it basic mathematics? Our second channel, the Gmaets 41 basic class. Yeah, that channel teaches you all of your basic concepts. That, of course, knowledge you might also need to be able to handle other higher stuffs, higher learning that you're going to meet. Take care of yourself. Bye-bye.